So we've learned how to find the first derivative, and we'll now work through an application of finding the first derivative and what we can use it for. We know that dy dx is the rate of change, and I'll abbreviate that with ROC, is the rate of change of y. WRT is with respect to x. So dy dx is how much y changes as we change x, the rate of change of y with respect to x. If we had ds dt, it would be the rate of change of s with respect to t, and so on. Graphically, dy dx gives the gradient. Now, graphically means drawing graphs. So when we draw graphs, dy dx gives the gradient at any point. Okay, so best way to explain this is to give you a function, and if we had y equals x minus 3 squared plus 4, now I'll sketch that, and it's not particularly difficult. If you had y equals, it's x minus 3 squared, so it's like an x squared, so it'll be y equals x squared, looks like that. Now the x minus 3 all squared means that we move that graph 3 units to the right. If it was plus 3, you would use 3 units to the left. So the x squared graph now can be drawn over here. And then the plus 4 simply moves it up 4 units. Well, we'll draw that in a solid line to show that's the final graph. So that's y equals x minus 3 all squared plus 4. 3 units to it's moved y equals x squared 3 units to the right and 4 units up. Okay, so that's 3 and that one's 4. Now if we were to expand this out, we've got x squared minus 6x plus 9 plus 4, which is x squared minus 6x plus 13. Okay, dy dx for that function, 2x minus 6, derivative of 13 is this 0. So what I'm saying is that there'll be a 0 gradient means the graph is parallel to the x-axis. So if we find where this is equal to 0, so dy dx is the gradient at every point, we'll find where we've got 0 gradient. 0 gradient simply means that the tangent drawn to this graph will be parallel to the x-axis, and most of you will realise it'll be at this critical point here, 3, 4. So we get 2x minus 6 equals 0, and if we solve for that, take the 6 to the other side, and you get 2x equals 6, divide by 2, and you get x equals 3. Now that confirms what we thought, that if I was to draw the tangent at x equals 3, that line there will be parallel to the x-axis. So that's what we mean by 0 gradient. Any tangent I draw on this side, you know, as you go from left to right across the Cartesian plane, if a line is falling, it has negative gradient. So everywhere when x is less than 3, so x is less than 3, dy dx is negative, and you could substitute in any value x less than 3, you can go 2, 1, 0, -1, -2, or any decimal in between, and you'll find that dy dx will be equal to negative. And then when x is greater than 3, dy dx is positive. Now, positive gradient means that the graph rises as you go left to right, and so all these blue tangents to the curve here, they're going to have positive gradient. In other words, the curve will have positive gradient when x is greater than 3. Now, it's important that we realise that when dy dx goes from negative to 0 to positive, as we have here, dy dx is negative, 0, positive, we have a local minimum, and it is also called a turning point because the gradient goes through 0. So from negative, 0, positive, we have a local minimum, and it is also a turning point. When dy dx goes from positive to 0 to negative, we also have a turning point. In this case, it'll be a local maximum. In addition, if dy dx goes from positive to 0 to positive, or from negative to 0 to negative, in other words, the gradient does not change sign, then you could have, not necessarily, could have what we call a point of inflection. And we're going to talk about these at length a little bit later. But what basically is going on in this case is that we get a graph that may look a little bit like this. So the gradient is positive here, the gradient is 0 there, the gradient is positive there. And so we may have a point of inflection, what we call a POI, at this particular point. All right, so we're going to, now next little talk we'll go through curve sketching and finding turning points, what we call maximums and minimums, and we'll use this information next.